she gets locked up and just have to put up with it.
Okay, so will you be
Okay,
here
it's
to measure the
recording. I could stay for a few minutes.
Just stay 2 minutes.
Wrong one.
Share. Sort of vaguely remember this from 2020.
Okay.
Presentation. First.
Let's,
Beautiful. Look at that.
where's the remote gone? Oh, is it working?
It is now.
Okay.
Okay. Thanks, Dan. Okay, so good evening, everybody. I'm hoping people at home can see me. I tend to move, so forgive me if I do because you're concentrating on your presentation, not on me. And this is going to look like a really quick and easy lecture.
Right.
If you heard what I said last week, this is also quite a difficult one. Okay, so we'll see how we go. We're only looking at very simple things. We're looking at uniaxial and biaxial gemstones, so doubly refractive. We're going to look at optic character. We looked at a little bit of that last week. We did not get an optic sign last week at all, but we'll do that this week. And we're going to look at something called an optical indicatrix. That's the fun bit. So last week, construction of a refractometer. Highly examinable, regularly examined, both internally at mid-year and the Board of Studies absolutely adores the refractometer. You need to know this. How do you look after it? Its limitations, that comes up. And things like the use of light. How do you obtain readings on singly refractive we did last week, and spot readings. So just quickly, my favoritist diagram. So let's have a look at it. So the refractometer, effectively a box with a lid that flips up, an eyepiece down here somewhere, come on eyepiece, and a polarizing filter. Actually, I'm better using it on that, I think. Okay, we have light, and interestingly enough, these things are drawn in yellow. Any idea why?
These things are what?
Well, we've got a light source coming into our refractometer. Why would somebody draw this in yellow? Yellow light, sodium light, I'm hearing good things. Something starting with an M. Monochromatic light, brilliant. Can anyone come up with the wavelength of this monochromatic light? Brilliant, 589.3, because it's the average of a yellow emission doublet at 589 and 589.6. So we average it. And those nanometers are so tiny, the units in which we measure it, we might as well call it one wavelength. Why do we need monochromatic light?
Standard.
Yeah, that thing. Take it a step further, Jamie.
I don't know.
Oh, come on! What's that thing called when you read it off the scale of a refractometer? Shadow
Line.
Shadow line, shadow edge. So, okay, one wavelength of light. We want a really sharp shadow edge. What happens if we use white light?
You get the you get a scale of the rainbow.
Scale of colour.
Yeah.
What colour do? Is that where you're going?
Yes.
Yeah, you get the colour fringes. And it's really hard to just read off a yellow line from that. Why did we decide to go with that yellow light? Is that an Australian thing?
Worldwide.
It's worldwide, it's the universal standard. So if we're talking about RI using that particular wavelength of light, we can talk about that RI to anybody in any other country. They're all still going to use yellow light. Okay, so we've got yellow light, it's monochromatic, it's pretty much a single wavelength, and it's reflected off a mirror. Whoa, back you go, you naughty thing. Off a mirror into a prism. Now I'm going to keep drawing hemispheres here. That's because all your other nodes have hemispheres. And things happen. It might hit the gemstone and the dot of RI fluid, and everybody who's just come out of prac has been putting lots of RI fluid dots all over your refractometer. And it might just get lost, gone. If that light disappears from the refractometer, you've got dark, haven't you? There's no light. If we come up to a ray that's coming in at the critical angle, remember, we're measuring it from the normal to the critical angle. It will get refracted, remember, right along that edge. Makes sense? At right angles to the normal. And a little bit gets to come back in. And that's exactly that delineating point. That's that shadow edge. Beyond the critical angle, all the light does what?
Reflect internally.
Yes, it's internally reflected. It stays inside the refractometer, and this is what gives us this lovely bright section. Okay? So we've got a dark section, we've got this lovely bright section, and these rays pass through a couple of lenses, a scale, and hit a mirror edge here, a reflective edge, and they're reflected back to our eye because we're looking down the eyepiece. Look at the dark bit. It was on the bottom, reflects to the top, okay? The bright bit was on top, it reflects to the bottom. So we get dark on top, remember reading your refractometer, shadow edge, light down the bottom. Fair enough? Okay, let's move it on. You'll see this to the death, this picture. That's that hemicylinder I'm talking about. Denser than the gemstone or less dense? Come on. The cylinder, it should be optically denser. It is optically denser, okay? So we have a gemstone, our RI fluid little dotty is there. The gemstone is in optical contact with our hemicylinder, okay? Critical angle, red one, light is refracted along that surface. That's the reflected ray which will give you your shadow edge, okay? And anything beyond is going to stay inside and be bright, okay? Just as the Kia said. So one last look at this. It all makes sense. You could draw it if you had to by now, I think. Enough? Okay. So, RI formula. Remember that formula N equals N1, subscript 1, sine of a critical angle, which is in combination between the gemstone and the cylinder. What we're finding is that if the critical angle increases, the refractive index also increases. This is gemstone in contact, very different from gemstone in air. And we will do a reprieve on that later. Gemstone in contact, critical angle increases, RI increases. And of course, if RI increases, critical angle increases, like this goes without saying. Now there are a lot more lines on this, so let's look at it. Let's get up to our critical angle, come down here, get our shadow edge, right? If we had a higher critical angle, much bigger one, our bright line would come all the way down here. See, it would be reflecting literally off that bottom bit closer to the edge. See how it's getting closer to that 1.8 something or other? Bigger critical angle, higher refractive index. So with a bigger critical angle, that shadow edge would actually be dropping. There would be much more of this dark stuff. Does that make sense? Back. Much more of that dark stuff, and you'd only have a little bit of bright stuff left. So critical angle goes up, shadow edge comes down, but down is a higher refractive index. Now, last week, we talked about gemstones showed single refraction. But you know about optic axis because Laura did this to death. An optic axis is the direction of single refraction in a doubly refractive gemstone. So it just behaves like a single ray in that direction. And that's important. If light goes down in that direction, it's not polarized. And we're going to go into doubly refractive gemstones today. So this is the slightly new stuff. Now you know if light comes in from air is anisotropic, hits a gemstone that is doubly refractive and isotropic, interchange those words, it's going to be split into two rays. Okay? We call that double refraction. You know that. If a ray of light comes into an isotropic material, what happens in that material? Does it split into two or three? What happens? If a ray of light comes into something, let's just say like diamond, does it get split up into two rays?
No.
No.
I'm hearing no. Why no? What crystal system does diamond belong to? Cubic. Singly or doubly refractive? So if that ray of light comes in, it just obeys Snell's law, stays as a single ray light. In a doubly refractive stone, it's going to get split into two. They polarized, vibrating at right angles to each other. Okay, this is all from stuff that Laura's done with you. So, doubly refractive gemstone, in comes a single ray, splits into two. They will travel at different speeds. They will be plane polarized and they will vibrate at right angles to each other. Okay? Still, revision. Did I say there was going to be something new today? Wait for it. Calcite ROM. Calcite is fantastic for showing double refraction. Okay? So if you draw a little dot on a bit of paper and put your ROM over it and rotate it, what are you going to see? Do you remember? You did it in class. Laura loves calcite. I've got calcite. You're all going to draw dots on bits of paper. I'm going to put a calcite ROM on it because I think, I don't know, you're asleep, you're tired, you have chronic. Draw a dot. Rotate a calcite ROM around it. And the answer's up there anyway. One dot will stay put. There'll be another dot that will look like it's travelling around it. Okay? Did you see that, Christina?
Yeah.
Easy to see?
Yeah, very easy.
One dot stays put. Another one runs around. So the dot that stays put corresponds to what we call an ordinary ray. A ray that's going to behave just as if it was singly refractive. Okay? That's the good ray. That's the ordinary ray. That's the well-behaved ray. The other ray is extraordinary. It doesn't behave very well. Have you met extraordinary people who always behave really well? Or do they break rules? I think they break rules. So this is the one that breaks the rule. Okay? And you get a little dot running around. Okay? One is stationary. That's the ordinary image. The other one, extraordinary image. So, again, more revision. So, the extraordinary ray. This is this little dot that runs around. That corresponds to that extraordinary ray. It's going to vary. It's not going to do the same thing all the time. Okay, so you've got your ordinary ray comes in, it behaves itself. It actually behaves according to Snell's law of refraction. Okay, it's going to have the same properties in all directions, same speed in all directions. It's a good guy. The extraordinary one is going to have different speed in a whole heap of directions. And remember, we talked about refractive index as speed of light in air divided by speed of light in a gemstone. So speed is going to come into this whole RI thing in a really big way. Calcite, you could also draw, your compass points if you like, and you'll find the same thing. Rotate it enough, and you're going to get something like this line here, which seemed, whoops, that wrong, that line there, which looks like it's only a single line, and yet all the others have got doubles. So that's the direction of single refraction. So if you looked for an optic axis, it would be there. There would be one optic axis. Is that uniaxial or biaxial?
Uni.
Okay, can anyone tell me what crystal system calcite does belong to?
Search it up and it's tetragonal.
It's what?
Tetragonal.
Whoa, look again. Calcite, anyone?
Cubic? No.
No, because hey, it's got an optic axis.
Oh, no way. It's trigonal.
Trigonal, thank you. Yeah, it's trigonal, okay? It's trigonal. And if you could imagine, if we chopped off a bit there, and if we chopped off a bit there, just nice little planes, and we look down in that direction, we'd only see one ray. Okay? That's the direction of your optic axis. And calcite's annoying because it always seems to be on the corners. Like it's never across that wrong. It's always corner to corner. Don't ask me why. It's just what calcite does. Okay, so you've got two images. One is stationary, corresponding to that well-behaved ordinary ray that doesn't break any rules, obeys Snell's law. The other image will move because it corresponds to that extraordinary ray which wants to go at different speed and it wants to break a few rules. We've talked about this. If you chopped off the two corners, tilted it up and looked down, you'd be looking down the optic axis. So far easy? So where the image doesn't move is the optic axis, single refraction, where the ordinary and the extraordinary ray behave the same way. Still revision, you're all over it? Good, because I'm pretty certain I'll stop boring you. One direction of single refraction, uniaxial. What if there were two directions of single refraction? Uniaxial? Biaxial. Okay, you're over that one as well. So, uniaxial materials, there's going to be one ray that's the good ray that behaves. There's going to be one ray that's extraordinary and wants to break all the rules and jump around. Important thing to remember. This is where it's going to get interesting. You know how we talk about light and we say we have a wave model for light? We also have a particle model for light. Light is also part of the electromagnetic spectrum. So we could look at a model of energy. We model things to try to understand how they behave. And so in gemology, and particularly with this stuff and the refractometer, we try to model how these rays of light are going to behave. So I'm going to suggest something. If you turned on a bulb inside an isotropic material, remember isotropic, no optic axes, no naughty rays, everything obeys Snell's law. Light travels the same in every direction, doesn't it? Like in diamond or in fluorite or in the garnets, yep. So if I turn on a bulb of light, for a millisecond, the light's going to go zap, zap, zap in all directions. How far will it travel in each direction? Different distance or same distance or very how?
Same distance.
Same distance. Can you imagine this? Light bulb just turned on for a fraction. And one ray's going to go there, one ray's going to go there, one ray's going to go up. The minute you stop that light, that's as far as it got, and you've got effectively a sphere. Does that make sense? Okay. So that's how we model the behavior of light inside an isotropic material. Same speed in all directions, same behavior in all directions, same endpoint. Okay, so it's going to look something like a ball. Same in all directions, create a sphere. Okay, and this is what we call an indicatrix. It's effectively a model of what that light is doing. So if your bulb goes on there, stops, light went that far, same distance, same distance, same distance in every direction. Okay, that makes sense? That's your ordinary ray, well behaved, same speed. And if light's travelling at the same speed through a material, there's only going to be one refractive index. Because remember, the two actually have a relationship between them. Now, what happens in a uniaxial stone? Well, in a uniaxial, we have the good, well-behaved ordinary ray, and then we've got the extraordinary one that doesn't want to obey rules. So the ordinary ray is just going to behave like that light bulb in the sphere. Okay? The extraordinary ray, it's not going to go the same distance. It's going to break rules. And it's going to go different distances. But those different distances are going to be controlled by the crystallography, and if you like, by the way the atoms and molecules are stacked within that mineral. If you think uniaxial, you've got tetragonal, trigonal, and hexagonal. They all have a C-axis. They all have lateral axes, 2 or 3 or whatever, that are at right angles to the C-axis. Fair enough? And that construction is going to limit what that naughty extraordinary ray can do. And it actually makes it behave like it's inside a football. Okay? Let's have a look at it. If we draw the two together, we've got our sphere, we've got our football, and we get an idea of what's happening. Okay, now the football can be outside the sphere, it can be inside the sphere. But there are rules that even the extraordinary ray has to obey. Because if we look at this sphere, that's representing the distance travelled by the ordinary ray, the well-behaved one. If we look at this footy inside it, what happened here? Well, the ray of light travelled just as fast along the optic axis, fair enough, but then it slowed down significantly. Then it speeded up and travelled just as fast in the direction of the optic axis, and then, come back, it slowed down and started to speed up again. You see that? So the speed of that light creates the shape. That's one way of looking at it. Footy inside the sphere. Another way of looking at it is footy outside the sphere. So the sphere is still the same. And the VO just means velocity of the ordinary ray, or if you like, speed of the ordinary ray. Okay, so that bit's the same. But what's happened here is the extraordinary ray still goes at the same speed along the optic axis, but now it's really going to misbehave. It's going to go faster and faster and hugely faster and get way out. Then it's going to slow down and come back to the same speed. Okay, so same speed, travel the same distance, and then it's going to head out again and get faster. Okay, so there are two ways of representing what happens with a uniaxial material. Questions? It was a big hit for the last 5 minutes, wasn't it? Okay. We're going to keep coming back to this because the concept is good. And remember that your refractive index does have a relationship with speed. And that's why we're doing it this way. We're creating a model of what happens inside that gemstone. So let's have a look at some of our definitions. Now, you know RI, Snell's law, sine of angle incidence divided by sine of the angle of refraction. I want to talk about speed. And we did look at this earlier. Refractive index is equal to the speed of the light in air divided by the speed of the light in a gemstone. Now, the speed of the light in air, from our previous work, 300,000 kilometres per second, it is a constant. It's not going to vary. Air is air, sort of, at least at ground level. Okay, so it's going to be a constant. So our refractive index is inversely related to the speed of light in a gemstone. It's an opposite. It's an inverse. Imagine if this was a really, really, really huge number. You divide 300,000 by a really huge number, you're going to get a smaller RI. If you divide 300,000 by a tiny, tiny number, you're going to get a big RI. See the idea? If one increases, the other drops. If the other increases, the first one drops. It's an inverse relationship. So if we look at the speed of light, if the speed is getting faster, it's corresponding to a lower refractive index. Does that make sense? That's your inverse relationship. Faster speed, lower refractive index. Okay? And that will bring us back to our model. Let's have a look at a sum. This is familiar because you've done something very similar already. Last time we looked at diamond, we had a speed of light at 124,000 kilometres per second, and we came up with an RI of 2.419, and the good book says it's 2.417, and the word approximately was used. Well, this is probably a slightly better approximation to the speed of light in a diamond, but do we care? How do we get RI? We're going to take 300,000, we're going to divide it by that number and hopefully get a pretty accurate RI. And if you want to do the sums, please do them. If you're nerdy and you love arithmetic, go ahead. You could take my word for it, which is not wise, because I could be leading you up the garden path. So hopefully this is a familiar sum. Speed of light in quartz is a lot higher. Diamond is pure carbon mostly, packed in a tetragonal type array where each atom is linked to 4 others. It's tight, 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 and light travels relatively slowly. It's only 124. Quartz, silicon dioxide, not packed as tightly. Light is traveling a lot faster. Fair enough? So let's work out RI, 300,000 divided by 194,300, and we get the RI of quartz somewhere in that vicinity, 1.544, so it's about to 1.553. So quartz is uniaxial and it will have some varying RI. But look at what's happened. RI of diamond is bigger than RI of quartz, true? Speed of light in diamond is less, okay? So you're seeing that inverse relationship again? Okay, we get a higher speed in quartz, lower RI. A lower speed in diamond and a higher RI. They go up and down like that. Christina, don't fall asleep when we're done. Don't fall asleep. Because we're going to come back to this. And we're going to look at how speed and RI affect each other. So let's go back to this one. I know it says positive in quartz, but why? Our sphere represents a ray that's behaving. It's the ordinary ray, travels at the same speed, no issues. Our extraordinary ray only travels in the same speed along the optic axis. The rest of the time, it's slower than the ordinary. Fair enough? It doesn't get as far. If it's slower than the ordinary ray, it's going to have a higher RI, isn't it? Okay, and because this variable footy thing has the higher RI, we give it a positive sign. Look at the other one, calcite. There's our ordinary ray, there's the speed of our ordinary ray, we're representing it by our great big sphere. Extraordinary ray, yeah, travels at the same speed here, but here it wants to travel faster than the ordinary ray. If it's travelling faster than the ordinary ray, the RI will be less than that of the ordinary ray. Does that make sense? Opposite to fast, lower. And that's why we give calcite this negative sign. How are you doing? Okay. So, quartz. The extraordinary ray was slower. Remember the footy is inside. We said it was positive because slower, the opposite is going to be the plus. The footy is inside, and we give it a uniaxial plus optic character and sign. And last week we couldn't get a plus or a minus because everything was the same. This time it's different. So if we've got a positive uniaxial mineral, we know the opposite of positive is going to be the slow. The extraordinary ray is going to be slower, and the footy is going to be inside the sphere. Alternately, something like calcite, the extraordinary ray went a lot faster than the ray in the sphere. Because it's going faster, we're going to take the opposite and give it a negative sign. So we say it's going to be uniaxially negative. And we know the extraordinary ray was faster. The ellipse was outside the circle. So look at it again. This is the one. The ellipse is outside the circle. Okay. Travelling faster, we get negative for calcite. Uniaxially negative. Inside the sphere, travelling slower. Invert that, give it a positive for quartz. Who have I lost? Okay. Now, we also look at it another way, and you've been sitting in prac and you've been filling out your little charts with numbers. Another way of looking at it is, if your lower numbers move more than your higher ones, we're going to give it a negative. If your higher ones move more than the lower ones, we're going to give it a positive. And hopefully that will link it in together. Okay? We use symbols. We use Greek letters. So the ordinary ray, omega, depending on where you went to school, it's the last letter of the Greek alphabet and happens to be an O. And that's the well-behaved one. O for ordinary, O for well-behaved, same speed, light does the same thing in every direction. We use epsilon, this little back to front 3, E from the Greek alphabet, that's the extraordinary, that's the one that either wants to speed up or slow down, that's the one that does not want to be normal or ordinary. And it does not obey Snell's law. This one definitely obeys Snell's law. Okay, that's the well-behaved. So we say that if our extraordinary ray is greater than the ordinary, and imagine your table. You've written down everything for your ordinary ray was constant. Your extraordinary ray, the high one, moved all over the place. You got a positive, you got a uniaxially positive stone. Hopefully you're not testing biaxials yet. And if the lower one was the extraordinary one that moved, you would have said it was uniaxially negative, okay? So if out of this whole presentation, this is the only thing you remember, you've got hope. If you don't remember that, it might be a little difficult. Okay. We know all of this. We know that uniaxial stone, 2 light directions, 2 shadow edges. You've been doing this. One's constant, one's extraordinary. Okay, the constant is omega for ordinary. The extraordinary ray is E. This is a bit of revision. So let's try to relate it to what happens on your refractometer. Now, we're talking about uniaxial gemstones singly or doubly refractive.
Doubly.
Some people are awake, it's doubly refractive, it's got to be. Ordinary ray stays still, extraordinary ray moves, okay? So when you fire up your refractometer and you've done all the right things and cleaned all your surfaces, I saw people wiping over with meths today, I thought that's good. I saw people in gloves, that's even better. Carcinogenic, that RI fluid. If you don't have a polar filter and you look down that eyepiece, you should see 2 shadow edges. Yeah, sometimes it's really hard. And if you're finding it difficult, do a spot reading. Remember spot readings from last week? Stand a little bit further away, move your head up and down, look at that little blob that corresponds to the RI fluid, half dark, half light. That gives you an idea of where your shadow edges should be. Have a look at your shadow edges. Now, I think every prac teacher is going to teach things a little bit differently. You do need to get your polarizing filter onto that because we want you reading each shadow edge, and one of those is going to move and one isn't. And you need to know what's going to happen in a uniaxial stone. So some people say, pull your polarizer on, spin it around till you get only the low shadow edge. Some say spin it till you get the high one. It's up to you. But whatever you're going to do from now on, be consistent. Okay, and this is again another refrain from the previous year lecture. Hopefully your teachers have turned on the lights, they've warmed up, you've got a sodium light. You've cleaned your stone, you've cleaned your crystal, you put on your drop of RI fluid, and I think you're probably getting really good at it because you've got better droppers than I had. We had a little ball on the end of ours, you put a drop on, it's like a lake. That's why we used to pick it up. It was horrific. You pick up your gemstone with your tweezers, you put it down, your gemstones go like floating. Pick it up, wipe it off, put it back down again. You've got a far better dropper now, so you should be getting a tiny, tiny little bit of fluid. Place your stone on, obviously close the lid. Now you close the lid, have a good look at where those lines are, spin your little filter until you get one line. I prefer to write the higher reading first. Some people prefer to write the lower reading first. We don't actually care as long as you're consistent. If your filter's up there for your high reading every time, write your high reading in every time. If your filter's in the other position, that's the low reading, write your low reading. Okay, but it's important, you've got to be consistent. If you mix these up, you'll never identify a gemstone. Okay, so you've seen all of that. You know all your steps. And you've seen this to the death note, I'm sure. You know, rotate 45 degrees, rotate to 90, rotate to 135. Why don't we do one more rotation?
So it's the same as what we started. The same as where we started.
Yeah, exactly. It's going to be where we started. The same orientation. Why do it again? Unless you want to make sure. Okay. When we do our RI readings, and remember they correspond to the speed and the velocity, we can actually work out which way the gemstone has been cut. So for anyone who's in the jewellery industry and you're looking at rubies, and you will play with a dichroscope later in the year, and you look down one direction and all you can see is red, 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 ooh. You look in another direction, you see red and orange red. The direction where you see red, red, red is down the optic axis. And if you're cutting a natural ruby, that's the direction of your best colour. So you try to do that, you're going to get a fabulous ruby. If you're cutting a synthetic, synthetics are doped up with chromium to the point where they're so red they're ringing at you. and they're almost, fluorescing in daylight, you might be cutting with your table in a different direction because you want to get as much material out of your synthetic as you can, and you're still going to sell them. Do you really care? No. Okay. Laura has also talked about tourmalines. If you look down the optic axis of a tourmaline, you effectively have a closed axis or an axis of extinction. You look down there, you're going to see dark. If you've got a nice green tourmaline and you cut it with a table in that direction, you're going to look down the table and see a really dark stone. Might not be what you want. You might need to cut differently. Or if you've got a pale pink tourmaline, you might want to have the table so you look down that axis, you get a better pink. Okay, something like kunzite, if you've heard of that one, always in that vertical direction, in the direction of the growth of the material, better pinks. So it's important for us, okay? So this is all going to link up with those rays. So if we look at a gemstone with a table perpendicular to the optic axis, like that ruby I talked about, or like the pink tourmaline, you're going to see on your refractometer 2 stationary rays. And no matter how you turn your stone and take your readings, you're still going to get 2 answers only. Your top line will be constant, your bottom line will be constant, and that actually tells you which way the stone was cut. So I've popped a little stone in here now. We're not talking about light, we're pretending it's sitting on the refractometer. So still using this diagram, but slightly different concept. If you travel all the way around the small diameter of that footy, your reading's going to be the same all the way around, true? If you follow the sphere all the way around, your reading's going to be the same all the way around, and you'll get 2 readings. The same thing will happen here, except that, okay, that's your lower reading, that's going to be your bigger reading. And so when you go to put it on your table, this is the sort of thing you'll see happening. 1553, all the same. 1546, the lower one, all the same, because you're looking down the optic axis and those rays aren't going to move around. You need to write down the refractive index. You look at the lowest one you can find, 1.546. You look at the highest one you can find, all the way to 1.553, okay? And then we look at a birefringence, which really is the top one minus the bottom one. If you want to do this with a calculator, fabulous. I cheat. I go something like 53 minus 46 is 707, 0.007. And you do need to write it to 3 decimal places. We always give our birefringence to 3 decimal places. Even if there's a 0 on the end, you put it down. Now, we've got 2 constant rays, and that can only happen in a uniaxial gemstone when you're looking down the optic axis. So we know it's uniaxial. But can we determine which one of these lines moves more? Christina's saying no. Can you see this top one moving? 5353, did it move? 4646, did that move? Nothing moved. So from the data that you've collected, you have to say that you cannot determine the optic sign. Please don't put not applicable. Next year's prac teachers are not going to like that. Okay, it's not that it's not applicable, it's just that you don't have sufficient data to determine what it is, okay? These notes are going to appear all the time. If the higher numeric value varies, you've got positive. If the lower varies, you've got negative. Didn't help us. But what we do know that if this is what you get, The stone is cut with the table perpendicular to the optic axis direction that way, table that way, and the two shadow edges are separated by maximum birefringence, full birefringence. And that's what you would write.
For when stones are getting cut, is it the closer that you're getting for it to be right on the optic axis? Would the numbers, would the variable increase or decrease from the distance?
If you
you
moved
are to
it?
the- Yeah.
Oh, absolutely.
So the closer you
Yeah.
are to it being cut right on the,
You look for some stones just to get a better result,
yeah.
a better colour. You will try to do this.
Yeah.
Sometimes you're just going to cut for maximum retention because, for example, rubies are expensive and you might get a much bigger stone, and at the bottom, you know, at the end of the day, you're looking at price as well in the industry.
Yeah.
So you might get more money for a bigger ruby than if you cut it in that orientation. Okay, so sometimes people will cut for retention. If it's a really bright red ruby, probably cut it anyway. Just get the maximum out of it. It will depend. It depends on the colour, depends on the quality, depends on the clarity, which is really important because clarity will give you total internal reflection and a better performing gemstone. Yep. Okay. So we can graph this if you want. If you like pictures, they will look the same. One straight line, one other straight line. There's nothing, it's not mind-boggling, is it? And I love this photo. Laura takes good pics. And this is, of course, a uniaxial gemstone. There's its table. I draw them upside down, doesn't matter. The table is perpendicular to the optic axis. We get one reading, we get another reading, both constant. And I like the comment here, very difficult to determine optical sign. Well, it is. You can't from that data. You actually take your stone, flip it up onto a pavilion facet and take a few more readings and see which ones move. Then you can work it out, okay? So there it is. Remembering also, come back. Where did you go? Good grief. No, I want that one. Remembering also that your crystallographic axis aligns in direction with your optic axis in uniaxial stones. It's the same direction. And so that's why that little stone's positioned that way. Okay, so table perpendicular, two sets of readings, both constant. If you get two sets of constant readings, you've got a uniaxial stone. Okay, don't panic, it happens. Cutting parallel to the optic axis. So your table's not going to be that way, it's going to be that way. Maximum retention in nasty synthetic rubies, absolutely. But also really important for things like tourmaline because of that closed axis. So what do we have here? We get your ordinary ray. It's got to be stationary, hasn't it? It's ordinary. It's boring. Your extraordinary ray is going to move this time, but there will be a meeting point. And you will find a maximum birefringence. So let's have a look at this. Gotta love this again. Now remember, this is side on now. So if we look that way, we're going to see a footy. They'll coincide, and then we're going to see our constant. Okay? So something's going to move. There will be one point where the readings are the same. If you start your 0 there, 45, 90, 135, you would come back to 0 there. You might not start there. You might start somewhere like here, meet up there. You might start here, meet up there and keep going. We don't know where it's going to start, okay? But you will get one reading that's going to be similar. And in your results, you'll see that. So when you get to this point, 641 all the way through, tells you it's uniaxial, you've got one constant line, right? The bottom line varies, 621, 32, the same, 638. When you get a top and a bottom reading that's the same in a uniaxial stone, you can conclude that it's cut with the table parallel to the optic axis. And then you'd still write down the same things. What is the lowest number here? Well, it's this one, 1.621. What is the highest number? They're all the same, 1.641. What's the difference between the highest and the lowest? 41 minus 21 is 20. But you've got to write 0.020 if you write a 20. Not good. Uniaxial because you've got one line that doesn't vary. And the bottom line varied the most, so it's going to be negative. With me? Everybody, nobody? Christina's nodding. I'm getting nowhere. Everybody's asleep. Jamie, look at me and smile, please. Somebody let me know you're alive. Okay. So same comments. Higher gives you positive. Lower numerical value varies the most. What's the only one that's varying? It's going to give us a negative. U negative. And this stone is cut with the table parallel to the optic axis. One pair of readings is the same. And from top to bottom is your maximum birefringence for that stone. Okay? Now, Gem 1 number is going to ask you to actually identify your stone. But you need to be able to do at least that much. When you graph it, bidding, something coincides, there you go. Another one, still a uniaxial gemstone. How do we know it's uniaxial from those figures?
Because one of them stays constant.
One line stays constant, okay? Uniaxial. The other one can move as much as it wants or as little as it wants. So our bottom line, 54, 54, 54, write it down, all the way through to what's the highest number here? 1670. Do your sums. 70 minus 54 is 16. Write it properly, 0.016. We know it's uniaxial. Does the top or the bottom move the most? The top moves the most. So it's going to take a positive, okay? How easy is that? Okay. We've got two readings the same, cut with the table parallel to the optic axis, and the highest birefringence is there. Okay, 0.016. And again, if you want to, you can graph it. This time, notice the top one moved more. Is that pretty simple? Because at the end of the day, you're going to take readings. You're not going to worry about an indicatrix, are you? No, only Laura and I get nerdy about that. Never mind. So if it's parallel to the optic axis, have a look at your footy. We either go around the footy or we go around the circle. That's all that's happening there. Okay, so there's going to be 2 points, top and bottom, if you like, where they're the same. Somewhere in your reading, you will have your two readings the same. Okay?
So we won't get anything about indicatrix in the exam, is that what you're saying?
Okay, so I'm actually working very much from Laura's PowerPoint.
Okay, sure.
Okay, so I think indicatrix is a really good way of explaining how light behaves, but it may be just that little bit beyond the course. What is examinable is what's in your lesson notes. And I haven't found an indicatrix in there, but we've been teaching this at least for the last 8 years that I'm aware of.
But it helps understand it. I just wanted to know whether I need to.
That's my question.
No, absolutely not. Look, a lot of the stuff that Laura does will take you that step further. Okay, and that's good teaching. But the other thing I will add about exams is since they're pretty uppermost, so this is the bit you will wake up for if you've been asleep. You can get bonus marks in exams. Oh. Aha. And I'll give you an example.
Yeah.
So we're sitting around in the library marking Gen 1 papers. And we tend to mark, like I might have been marking question 2 and 4 or something. We split it up and then we double mark. So there's a bit of rigor in how we mark papers. And I'm marking a paper and there's this brilliant answer. Laura's sitting opposite me. I go, Laura, have a look at this answer. This is amazing. This is so good. I reckon I'm going to give it an extra half mark. Laura looks at it and goes, oh yeah, if you want it. I get to question 4, whatever, marking, and another, and we don't know whose papers they are, right? Because everything's coded. You get a number. So we don't know whose it is. Marking another question, and oh, my lucky day, I've got another person who's written a really fabulous response. So pass it off to someone else, go, what do you think of this? Worth half a mark, half a mark. At the end of the night, we tally up all the marks, and someone's done absolutely brilliantly, and it's the person who got the 2 extra half marks. And Laura's just about wetting herself laughing because she actually managed to sneak in and do the paper while she was supervising the exam. I was marking her paper. But it's not unheard of to give those bonus marks, okay? So it's possible, and just some of those extra things will help, okay? So I think we've done parallel to the optic axis, to the death. Most of the time you won't cut either way, because if you've done any gemstone cutting, sometimes you're cutting from just a weathered pebble that was found in alluvial ground. You look at it, you go, I've got no idea, stop it up, cut it. True? It's all right, we'll get Dad to do the course later. Sometimes you just don't know, and you might be cutting at an angle to the optic axis. And one time when you will always cut at an angle to the axis is in an orthorhombic stone. Although, well, you'll cut it at an angle to the basal pinacoid, not an axis, because you're going to tilt it. But if you've got perfect cleavage, you don't want perfect cleavage across your table and never polish it. It's like graphite pencils, you just keep taking another layer off, you're not going to polish it. So there are different orientations. What happens? Look, it's the same thing. Your stationary ray, well behaved, does what it's meant to do, not an issue. The ordinary ray will move, but they're never going to meet up. So if you've got 2 rays, they never meet up. One is stationary, you've still got a uniaxial stone. You'll still determine whether it's uniaxially positive or negative, judging by which line moves the most. But you won't necessarily be able to say, oh, it's perpendicular or it's parallel.
Sorry, did you say that the ordinary ray will move?
I did not. If I did, somebody's going to sack me.
The
The extraordinary, I may have done, the extraordinary ray will move. So if you look at this, and that's a typical example, there's your ordinary ray, 641, hasn't moved at all. Your extraordinary ray has moved. Those 2 red rings, I don't know, I'm nerdy about numbers, so I put them in. But it's still exactly the same sort of thing. Top to bottom, 41, 21, 21 to 41. Birefringence, top to bottom, 0.020. You're getting sick of these numbers. You've been looking at 1.621 to 1.641 all night, haven't you? Do you want to know what the stone is? Yeah, it's who's the tourmaline? Well done.
I just looked at one in the.
Sorry?
I just looked at one an hour ago. So.
Oh, you did? Okay. Yeah. Laura actually set me up when I was doing Gem 1. She said, go test this. And I'm like, I'm in Gem 1. And I get 1.621, 1.641. She said, yeah, that's all I wanted to know. Why did I test it? Tourmaline. Yeah, it's tourmaline. Birefringence. That sort of birefringence almost allows you to see doubling of back facets. Almost. Peridot, you'll always see doubling of back facets, but that's like a 0.036 or 37 or something. So that's got a huge birefringence. So birefringence is useful to know. If you get a 0.03 birefringence, suspect something nasty like apatite. You get a 0.0406, you've probably got a beryl, which I think you were testing a few today. So still uniaxial. The bottom line is the moving one, it's a negative. But we have got 2 readings that are the same at 90 degrees to each other. And that's a little bit of a hint that this stone was cut at a 45-degree angle to the optic axis. And not examinable, but I'm sure you'll get one somewhere. And if you say cut at an angle to the axis, we're going to go, yeah, that's terrific, full marks. If you then say, oh, but we've just had at 90 degrees to each other, two readings that are the same, it must be cut at 45-degree angle. Bonus, absolutely every time. Okay, these will never meet. At an angle, just put it in for good measure, and that because Laura likes them. Now, are you okay with uniactuals? One ray is going to be well behaved. It's a good little ray. Yeah, does everything teacher tells it to do. Same speed, same light properties in all directions, and you get your extraordinary one that needs to be different. Okay, that's uniaxial. When we get to biaxials, we don't have a well-behaved little ray. We have two rays that want to be weird and wonderful and do all sorts of fabulous things. And I'm not going to bore you with an indicatrix for biaxial. One, because I don't have one. Two, because if I did, the mathematics would be amazing, so I'd love to get one, but I won't do it to you. So we've got two optic axes, two directions of single refraction, but we're just going to take measurements in exactly the same way we used to. Now, the thing here is we now have three vibrational directions. Incoming ray of light split into two, vibrating at right angles to each other. You look from a different direction, you get a third ray. So biaxials are a bit more difficult. And when you consider the crystallography, you know, suddenly things get squished and pushed over, and when you look at your crystals. So we have our three rays, X, Y, Z, fast, intermediate, slow. We give them Greek letters, alpha, beta, gamma. Why wouldn't we? You know, you did algebra in probably year 8, and it was all ABCs. As you progressed through the years, it all became Greek. So we talk about alpha, beta, and gamma, and the same rules. Okay, you write down your numbers. You look at your higher line. If your higher line moves more, it's a positive. If your lower refractive indices move more, you've got a negative. Okay? We also say that if the Ri corresponding to beta is closer to alpha, you got a positive. If it's closer to gamma, you got a negative. And frankly, you're never going to map those, but I think it's in the notes. So if you look at something as obscure as sillimanite, and interestingly, I was just up at a mine in North Vietnam together with Laura, and it was a place where they mine ruby and sapphire and spinel and sillimanite. Don't ask me. It's such an obscure stone. I have a great big yellow one at home. Yellow, yellow, yellow. Couldn't wear it. I'm not going to bother. But from the blue book, we get all this fabulous information for sillimanite. We get the refractive index. Okay, couple of edges, a birefringence that varies, an optic sign this time, both top and bottom varied, so it's going to be biaxially, it's positive, beta was closer to alpha. And if you have a look at what beta and alpha were, see how from 61 to 70 is a jump of 9, from 70 to 84 is a jump of 14. This was actually closer. So beta was closer to the top one. Just to illustrate that point, you're not going to be looking up Wikipedia in your exams, nor will we examine it. But we'll examine this. So let's have a look at this. You're doing your reading, you're writing them all down. You're writing them all down. 70, 74, 80, 75. It jumped around a bit, didn't it? And in fact, it jumped around from 70 to 80. So that's a difference of 0.010. Quite a bit of jumping around on that one. Look at this one, 61, 63, 68, 59. The lowest was 59, and it jumped up to 68. So the difference there was 0.009. Which one moved more? Top or bottom? The top moved more. Positive or negative? Positive, because the top line. So it's the same principle. It's the same principle that you had for those uniaxial stones. Whichever line moves more is the one that's going to give you your optic sign, your positive. Okay? Once you've written those down, calculate your birefringence exactly the same way. 80 minus 59, 21. Write it properly, 0.021. It's biaxial because both sets of readings show movement, okay? And positive because 10 is a bit bigger than a 9. Fair enough? So nobody's going to ask you to model biaxial stones because that gets really difficult, but they will ask you to interpret your findings, okay? And here, just to prove a point, if that's going to be my beta edge, it's definitely closer to alpha. We got the positive. But again, alpha, beta, gamma, I think it's in there, but. So let's play a little bit. You might need to get pen and paper. These are readings from a refractometer. So we've got 48, 45, 44, and 46. Which is the smallest one? 44. Which is the biggest one? So what would you write here, the difference? There's a 4 on the end. 0.004, okay? These jump around 38, 39, 40, 35. Which is the smallest one?
35.
Which is the biggest one? 40. So what difference would you write here? 5. Okay, so you had a 4 up here and a 5 up here. Which one moved more? The bottom one. So positive or negative?
Negative.
So you'll have a B negative. Both lines move, so it's biaxial. So optic character, you'd write biaxial, optic sign negative. And what would you put for your RI? What's your smallest number? 1635. And what's your highest one? 48, that one? Yeah, so 1.635 to 1.648. What birefringence did you get?
0.013.
Well, let's check. There you go, look at this, 4, 5, written in, perfect, biaxially. You can interpret, can't you? Was that hard?
No.
Okay, well, last one. You thought you were going to get away that easily. Okay, so this is what you got. 701, 699, 696, 702, they all move. 92, 94, etc., they all move. Uniaxial, biaxial? Biaxial. Okay, both move. Let's find the difference. 01, 99, 96 is the lowest?
Yeah.
What's the highest?
02.
02, what's the difference?
008.
6.
Oh, 6. There we go. Quick maths.
You are allowed to use a calculator. Look, I hate arithmetic, it's not my thing. Okay, it's a 6. Now we've got 92, 94, 91, 95. What's the lowest one?
91.
What's the highest one?
95.
5 minus 1 is?
4.
Okay, you had a 6 and a 4. Which one moved the most?
Top.
So we're going to have plus or minus here.
Plus.
So biaxial plus because the top one moved the most. Refractive index, what's your smallest number? 91. What's your highest number?
02.
02. Anyone work out birefringence?
0.009.
I believe you. I'm not going to do maths, not standing in front of this lot. Optic character, isotropic, uniaxial or biaxial? Biaxial. What was the sign you decided on? Plus because that was a 6, yeah?
I was going to say your human calculator, but then.
Yeah. No,
Did that make sense?
Yeah.
You know how to do it?
Yes.
Do you want any more torture?
Yes.
Oh, come on.
You get a summary. Okay. Isotropic, semi-refractive, how many optic axes?
0.
0. Put your light bulb, it creates a sphere, right? Does anything move on the refractometer?
No.
Boring, boring, boring. Top line will be the same as the bottom line, no movement, it's the same in every direction. Fantastic. Anisotropic means doubly refractive. Okay, uniaxial, how many optic axes?
1.
Because it's on the board. Thank you. How many lines move on the refractometer?
1.
1, because it's on the board. And 1 will stay
Same.
the same. If you see one that stays the same and the other one moves, you've got a uniaxial stone. Biaxial optic axes,
2.
what happens to both of those lines?
Remove.
They should be moving. Okay? So refractometer is important. I know there's been a ton of repetition. But you got me. Laura would have repeated more. Truly. So please, please be on top of refractometer. It is one of the most powerful instruments you use in the lab. Okay? What's it limited by?
The refractive index of the fluid.
Brilliant. Exactly, which is approximately what?
1.81.
Okay, so you get your blue book. RI of the fluid is somewhere here. You don't have too many stones with a higher RI. But that's when things like specific gravity kick in. And that will help you identify the stones. And hopefully next week's going to be SG. I'm not sure.
We're doing, in here. We're doing dichroscope next door next week.
Oh, so we might be doing colour. My favourite subject. Absolutely my favourite subject. Okay. Tutorial on the 12th. It's a Thursday. Does that really stuff anybody up?
Yes.
Can you come online?
Yeah.
What time will it be?
It'll be 7:30.
Yeah.
Okay. Can
Yes.
do.
Yeah, online.
Will it be able to be viewed after? Like I work a night shift on Thursday, Friday nights. So I start at 3 p.m. finish at 9 a.m. Like I work at school, I get to sleep. But there's no opportunity, as long as it's recorded. Then I'll probably-
We tend not to record tutorials, but we could. Just ask Laura for that.
Yeah.
Okay, remember Laura's boss.
Yeah.
You know, I'm her succession planning. I keep saying to her, you want succession planning, you get somebody who's younger than your mother. So it works like that. So the 12th, remember it. We're going to try and get your workbook up at least with 2 weeks to do it in, because like really you need time to do it. There will be instructions like draw. I quote David, draw means draw. I'm sorry, but in an exam we still do it the old-fashioned way, so you will be drawing. Draw all your instruments, learn to draw them, okay? Refractometer, I'll give you a hint. If you can draw your rays of light back to your ocular, you can draw your ocular, you can draw your prism and your gemstone, and you can work backwards, okay? If you've got to draw a refractometer with any sort of line, come in from your light source, off the mirror, up to your gemstone and your RI fluid, back through your lens, scale lens, back out to your ocular, okay? It does help to do it that way. And put the box around it. Everybody starts with the box. Think outside the box. Do the rays of light first, you can put your box later. Who cares if it's a bit out of shape? Make sure you've got a delineation between the lid and the box, like the lid opens. Okay, wanted to know. Any questions? Please.
The PowerPoints that's uploaded in the Moodle is from 1st of May.
Correct.
I noticed that some of your slides are different. Would we get your version in here?
It's coming. Okay. Look, the difficult thing is to deliver somebody else's lecture. So this is very much Laura's work, and all power to her. Maybe I like to rearrange things a little bit, just to follow how my sense of logic works. And I take it that everybody's sense of logic is going to be different. Okay, so if it helps you to have 2 PowerPoints, I know David's going to do that, he promised me. And if he does it, you're going to chase me, aren't you?
Yeah.
All
You're
right.
easier to chase than David.
Pardon?
You're easier to chase than David.
Oh yeah, but I chase David really well.
And is it okay the tutorial can be online as well on Thursday?
Tutorial can be online. If you can humanly come in, because you'll find that Laura and I will both be in hopefully by then. And we both tend to reteach material. Online, you might just be asked to respond to what you've done. Okay, so I run tutorials very differently from everybody else, but I guess, I just do. And Laura always comes in with a whole heap of additional material too. So if you can come, come. If you can't, okay, we understand, and please make sure your work's handed in reasonable time, because Jamie, I still owe you some annotations. You gave me one, which I haven't even looked at because I have been overseas, but I'll come back to it. If you can hand your work in, and if you're with me, I'll certainly give you feedback. Okay? So please do it. Please don't hesitate to ask questions. And bon voyage, mes amis. Be safe. Okay? Cheers.
Thanks.
You're welcome. Okay. I might just opt out here. Just give me 2 seconds.
Visitors are in the meeting. What the fuck is this?
You just wait here. She will let you in. Order the food so I can go get it.
Oh, yeah, sorry. Oh, straight to Hyderabad.
So किसने जाना है vet?
दोनों को जाना है, बट हंटर का ये लगाना है ना, अगर वो सैंडी को बरांजा मिल गया तो नहीं ले जाएंगे, सैंडी के लिए वेट करेंगे। अगर बरांजा वो नहीं लिया तो इसको बरांजा लगवाना ही पड़ेगा। और इसकी ये एक्जिमा के लिए ये देखो लेग और टेल सब खा के ये कर रही है। आई हैव टू गेट दैट चेक्ड। शी इज टोटली डिजीज्ड इनसाइड हर स्किन।
She'll just need an injection.
Yeah, I want.
Like I've seen this.
Yeah.
Get.
Yeah, so you have please talk to them because I have had a fight with them.
They're just gonna ask like gold bills. You know, if you are paid it.
No, not there. वहाँ पे नहीं. Huntingdale 136 लेते हैं बरांजे के लिए. वहाँ 165 लेते हैं और वो 150 लेते थे. उनका भी ये सेटअप करना मेरे फोन पे every 2 weeks मेरे पैसे जाने के जैसे प्लीज. एक मिनट. Halim, chicken curry combo, chicken tikka, non-veg thali, नहीं, चावल है. What is this? कैसा है माल?
It's nice.
Not bad. I mean, it's better than all the shit crap.
I mean, it's nice.
Chicken curry rice. नहीं हाँ मुझे चिकन खाना है साला ओ मेरा ये बंद कर रहे हैं मेरा सेंटर लिंक
Why?
क्योंकि I've had too long I've used fucking they're gonna do some job assessment shit in 3-4 weeks. I've had too long. I've had what you call health certificate. What's that? Medical certificate. I can't do that anymore.